Hello, everyone. I'm Zibing Yuan from South China University of Technology. Today, my talk is about two main origins of intermediate volatile organic compounds, just IVOCs emissions from vehicles in China. Ozone is increasing significantly over recent years, along with the dropping of all the other kind of pollutant. VOC is one of the most essential precursors of ozone in China. And actually, by extracting a very classic figure from Professor Xiaomin's study, we can see that VOC actually is the fuel of the atmospheric oxidation. You have more VOC, the ozone formation will be faster. In China, especially in urban area, we know that vehicle exhaust, vehicle emission, mobile emission is a very significant contributor to the VOC emissions. From 2002 to 2005, the number of vehicles in China increased dramatically with an annual average growth rate of 9.2%. However, due to very stringent emission control measures, we see a continuously decreasing trend of pollutants, including CO, total hydrocarbon, NOx, and PM. Annual average decrease rate is about 2.6%. Overall, China has the largest number of vehicles in the world, so we expect China will contribute significantly to the VOC emissions. Currently, investigation on VOC emissions from vehicles is a research frontier. There are measurement methods to study VOC emissions, for example, the tunnel study or the smoke chamber measurement, chassis dynamometer measurement, and also the actual on-road condition measurement. All these kind of measurements have been widely used to study vehicle emissions. However, a very important limitation of previous study is that previous studies mainly focused on non-methane hydrocarbon, just the hydrocarbon CH, while they largely neglected oxygenated VOC and intermediate VOC. So they cannot give a full picture of the VOC emissions from vehicles. So what are IVOC? IVOC are compounds with effective saturation concentration of 10 to 3 to 10 to 6 milligram per cubic meter, with their volatilities lower than those of VOCs. So they correspond to actually alkanes with carbon number of around 12 to 22. Okay, if you increase the carbon number further, you will go to semi-volatile organic compounds. And then if the carbon number is larger than 34, it will go to totally in particle phase. And previous study has also demonstrated that IVOCs were responsible for about 50% of SOA formation from gasoline vehicles and more than 95% of diesel from diesel vehicles. These figures in a study in California. That is because the IVOC emissions is very limited worldwide. Most of the studies were concentrated just only in the US or in China. Characterization of IVOC emissions quite challenging. There are two main challenges on the IVOC emission characterization. One is for sampling, because IVOCs from vehicle exhaust are mostly emitted in gas phase. However, we cannot measure because they have a very high temperature, more than 100 degrees. We cannot measure it directly. We have to measure at the normal temperature, but they will go through gas particle partitioning at normal temperature. So we have to conduct simultaneous sampling in both gas and particle phases for a comprehensive picture of IVOC emissions. This is for sampling. The other challenge is for analysis, because over 80% of the total VOC cannot be identified at a molecular level by traditional spectrum instrumentation. We have to find ways to quantify the total IVOC contribution. So the current status is that the formation processes of a VOC from vehicle exhaust are not quite clear. Impact of tightening of emission standards of IVOC are not characterized because in the past decades, China has tightened its emission standards for multiple times. But what's their impact on IVOC are not well studied. And lastly, formation potential of SOA from IVOCs are not accurately quantified. Okay, in order to study these three important questions, we actually set up a very comprehensive experimental system, including a series of online and offline measurements. For the every IVOC measurement, we have a 10x tube behind a quartz fiber filter. In order to have the measurement from emission sources, especially from combustion emission sources like vehicle exhaust, which has a very high temperature, high humidity, and also high concentration, we have to build a very smart dilution system. And this dilution system has to be dynamic and adjustable because different kinds of vehicles may emit a vast range of concentrations. So the dilution system has to be dynamic and adjustable. It also has to be stable because we try to avoid the impact of gas particle partitioning because the dilution ratio can impact the gas particle partitioning directly. And lastly, it has to have appropriate size, cannot be too large. And this is to reduce the retention time in our system to avoid the VOC loss. Especially for those VOC with high reactivity. For the IVOC measurement, we measure gas and particle phase simultaneously. For the gas phase, we measure by a thermal desorption 10x tube behind the quartz filter. So in our sampling system, we collect the particle phase on the filter first, and then we collect the gas phase by the 10x tube after the filter. We analyze the sample by TD-GCMS. And we use this well-established method to quantify the IVOC mass and also different compositions of IVOCs, N-alkanes, PAH, B-branched alkanes, and also UCM, unresolved complex mixture. We cannot identify the specific species in UCM. We use this empirical formula to calculate the total mass of UCM. In this study, we tested 16 vehicles in total, including both gasoline and diesel vehicle, ranging from China 1, this is the oldest emission standard, to China 6, the newest emission standard. For diesel vehicles, we only covered China 3 to China 5. We used VMAS simple transient condition cycle to conduct our sampling analysis. This is the most prevalent method that can simulate the urban driving condition in China. And because IVOC emission is relatively little, so we conduct multiple cycles to ensure that we can collect enough sample for analysis. Okay, let's look at some of our findings. This slide shows the emission factor of gasoline and diesel vehicles. We can see that along with the tightening of emission standards, the total emission decreases drastically. This is in line with our understanding. Gasoline exhausts were mostly alkenes and aromatics, just the hydrocarbon part. The lower figure shows that intermediate VOC, the orange part, and also oxygenated VOC, the blue part, are the most important composition of diesel exhaust. For both gasoline and diesel, they decrease drastically. However, the emission factor of OVOCs and IVOCs did not show significant drop along with the tightening of emission standard. They almost in the same level in different emission standard. Well, percentage-wise, we can actually see IVOC and OVOC shows a significant growth along with the tightening of emission standard. For example, for gasoline, from China 1 to China 6, their fraction increased from several percent to 23 and around half of the total organic emission. For diesel, it's again the same. IVOC contributed more than half from different emission standard, while OVOC are more important for heavy diesel vehicles. IVOCs are more important for light-duty diesel vehicles. If we compare our finding with previous study in other parts of the world, we can see that the emission fraction of gasoline and diesel exhaust were comparable to their counterpart in the US. So let's look at the chemical composition of IVOC. IVOC have mainly four compositions: N-alkanes, PAHs, branched alkanes, and UCMs. And in their study, we find that gas phase IVOC from both gasoline and diesel was similar to its fuel. For example, you look at this bar. This shows the gas phase IVOC emission composition for gasoline vehicles. They are very much similar to the chemical composition of gasoline fuel. This figure shows the diesel vehicle. Our composition is also similar to the diesel vehicle composition to the fuel. So this is for gas phase. However, particle phase has a different picture. This is the particle phase in our study. You can see that for gasoline vehicles, particle phase, they are quite different from fuel. However, they are similar to the composition of lubricating oil. But similarly for diesel particles, this is for particle phase composition. They are different from the diesel fuel, but they are similar to lubricating oil. So this let us think that can gas phase IVOC and particle phase IVOC be from different origins because their chemical compositions are largely different. Gas phase IVOC are mainly from their fuel, while particle phase IVOC are mainly from lubricating oil. So let's look at the volatility distribution of IVOC. Let's look at the gas phase first. For the gasoline vehicles, they are mainly concentrated in bin 12 and bin 13. The gas phase emissions are very similar to the composition of gasoline fuel. For diesel vehicle emission, they are different from gasoline, but they are also quite similar to the composition in the diesel fuel. So the volatility distribution of gas phase IVOC from gasoline and diesel were distinct, but are very similar to their respective fuel. This suggests that fuel burning may contribute predominantly to gas phase IVOC. And then let's look at the particle phase IVOC. In the particle phase, we see a very obvious peak around bin 16 to bin 18. Okay, there's a peak for both gasoline and diesel vehicles. Okay, our previous hypothesis is that for particle phase IVOC, they are originated from lubricating oil. Let's look at the lubricating oil composition. They are different. There's a consistent increasing along with the carbon number. So this shows that lubricating oil is not the main source of particle phase IVOC for both gasoline and diesel. There are actually three main factors determine the volatility of particle phase IVOC. Well, the lubricating oil will firstly evaporate on the hot surface of the engine to become gas phase, and then nucleate or absorb on the particles, and then to go through the gas particle partitioning to origin, which is lubricating oil, represented by this blue line, and then it's the evaporation on the hot surface, which is represented by the red line, which decreases along with the carbon number, and then the nucleation or absorption, which is represented by the blue line, increase along with the carbon number. So here we build up a conceptual diagram to show the combined effect of these three factors. As a collective result of these three factors, the particle phase IVOC can be shown a peak at bin 16 to bin 18. This conceptual diagram actually further evidence that lubricating oil is the main region of particle phase IVOC. Okay, lastly, let's look at the potential SOA production. Well, this figure shows that the total SOA production along with the tightening of emission standard. Actually, SOA production of IVOC showed a generally increasing trend when we tighten emission standard from China 1 to China 5. Not until recently when China 6 is implemented, SOA production dropped significantly. user. So another very important information is that when we look at the ratio between IVOC produced SOA times POA, we can see that this ratio is above 2. That shows that the IVOC produced SOA almost doubled those emitted directly from the vehicles. So the much greater SOA contribution underscores the importance of controlling IVOCs from on-road vehicles because they will generate much more particles. These are the key messages of my talk. I think I have already covered all this, so I'll now repeat. Okay, yeah, thank you very much for your attention.